This is Algebra 2 with trig, 7.1, 7.2b. We're going to model exponential growth and decay functions. Mainly story problems here. We're going to first look at an exponential growth model. So we have our y equals a. A is the amount that we're starting with. If it's growth, we're going from 100% plus we're adding an amount of rate to it. So your percentage rate that it is increasing by. And then we have a time as an exponent, how often that occurs. A lot of times it's every year. So the A is the beginning amount, the initial amount. The 1 is that it's 100% plus extra. The R is the rate at which we increase by, and the T is how often we do the calculation, which is typically a year with most of these problems. So here we have buffalo in a state park. We're starting out with 38 buffalo. And it grew, that means it increased. That's exponential growth. So that's how we know it's a plus, is because of the word grow. By about 7% per year. So if it's growing by 7% per year, we're starting out with 38 of them. 1 plus 0.07, because that stands for 7%, but it's the decimal version of that percent. For T years. So we can simplify that down a little bit as 1.07. So if we're going to come over here and try to figure out the number of buffalo after 7 years, we're starting with 38. We have our 1.07, and we want to figure out how many buffalo are there after 7 years. If we're increasing by 7%, what is that going to be? So we're going to take our calculator, do y equals, we have our 38, 1.07 to an exponent of x. Now we can look at the table by doing second graph, and we can see here, this is how many we had at 0 years. Originally we had 38, and then that would be 7% more, and then 7% of the previous number, and 7% of the previous number, and so forth. So after 7 years, you could get your calculation that way. You could also get your calculation by saying 38, 1.07 to the 7th power gives us our 61.02. So we have about 62 or 61 buffalo. Now what we're going to do is use our graphing calculator to graph the model and estimate the year where we have about 30 or 53 buffalo. Well, we've already talked about how to get that into your equation. And if we hit graph just like this, we wonder, where is the graph? but that's because when time is 0, we're up at 38. So we need to be sure that we do our window change. We're not zooming in and out. We're doing a window change of a maximum that is going to be more than 38. All right, there it goes up. We want to know when we're going to have 53. Now, we're supposed to be figuring out 53. So I need to actually have a window that is going to show us a height of 53. I only put in 50, so I need to have a number that's bigger than 53. Otherwise, it's not going to show up on our grid. So we could tell that. So we need a number bigger than that. So now 53 should be coming through here somewhere. For the calculator to do it, we need to go to y equals and down to the second equation to type in 53. Now we can see where the two graphs are going to cross. And wherever that location is the x value of how many years it'll take to reach that amount. So we go to second, trace. We don't go to trace. We're not tracing, we're calculating. We're going to go to the intersection and hit enter. It asks us two questions. First of all, it says first curve. Is this the equation you want? Yes. Is that the equation that you want as your second one? Yes. And then it says guess. If it crosses more than once, it's important to be closer to your answer. If you want to get close to it, you can, but we know this only crosses once, so we can just hit enter, and it'll show you that you're at 4.92. So T equals 4.92 years. About 5 years for the buffalo to increase to 53. All right, you want to show your exact value because there are some misconceptions of not getting to the exact value. For one, you could have gone to table and looked at where 53 was. That's kind of close to 53. So you could have said, well, it's kind of like 5. It's about 5. That's not very accurate. We can be more accurate using a calculator. If you use the trace button, you can trace along there, but if you notice, you'll never get 4.92. So if you give me an answer that is 4.89, then you know that you did a calculation that wasn't as accurate. So you want to be sure to follow the steps for the accurate calculation. All right, so that is exponential growth. We are growing at a 7% rate for these buffalo. Now we're going to talk about compound interest. Compound interest is related to money. We have A that you could say stands for an account. Your account has this much money in it. P stands for principal. We have 100% of our money, plus we're going to have R, which is the annual interest rate. And we divide that by N. You're taking that interest rate and you're going to break it into little pieces. N is a number of times compounded per year. How often are you compounding it? Are you compounding it once a month, once a week, every day, every second? Okay, and T is going to stand for your years. It's the time that you're doing these compounds in, and the T is years. So we're going to have a savings account, and we're saving money for our first car. You're going to deposit $2,900 into your account, and your account pays 3.5%. Find the balance after 3 years if the interest is compounded annually and if the interest is compounded monthly. So 2 different questions. So we have our account amount, and we are depositing in $2,900. We're going to get more than $2,900 because it's 1 plus. Our R value is 0.035. You've got to move the decimal spot over 2 when you're turning a decimal. I'm sorry, turning a percent into a decimal. Now they want us to compound it annually. If you're going to compound it annually, you don't really need to use a compound interest formula because you're just dividing by 1. And it's 1 times your 3 years. So the ones are pretty irrelevant. So really, this now goes back to your exponential growth equation. So we have our 2,900. $1.035 raised to the 3. So in 3 years, without putting in any additional money and only having a 3.5 interest rate, you will increase to $3,215.28. The bank gives you that extra money just because you have your money there. And typically the bank actually uses some of your money and does some own investments with your money. And that's why they end up giving you money back. That's where that money comes from. It doesn't magically just appear. They invest your money and they give you a cut of that at 3.5%. Monthly. Now, if we're going to compound monthly, we've got our 1 plus our 0.035. If it's going to get compounded monthly, we're going to divide that 3.5% by 12. We're cutting it up into 12 equal amounts. You don't get your 3.5% every month. That would be outstanding. But you get your 3.5% broken up into 12 equal amounts. So some people think that there's no difference. Here, we're not going to see a big difference, unfortunately, because we're only talking 3 years and we're not putting additional money in. So it's not going to be a big difference, but the point is there is a difference. So the first thing we're going to do is look at what does it mean to be 0.035 divided by 12? So each month you're going to get a 0.0029. With an exponent of 36. So that's 2,900, 1.0029. And that will approximately be 2,900. Now you could do 1 plus your answer, and that would be very accurate. But going 4 decimals is more than enough to go out to the number of cents that we need to do. So if you're more comfortable with just putting in your 0.0029, it's not going to be a deal breaker. And we're raising it to the 36. So that's giving us $3,218. And 64 cents. So not dramatically different, but compound interest does increase the amount that's there. What's happening is they're giving you money after the first month. Not a lot of money, but they're giving you a little bit extra money. So now your account is worth more than 2,900. And then you get your 1/12 of your percent on top of that more than 2,900. And you keep doing it on more than the previous amount. And that's why you actually have more money in the end, even though you still have the same percentage rate. Now let's work it backwards. What if we want to save $2,500? In your account, and the amount that you should deposit, that's what we're trying to find. The account is going to pay 4%, so that's 0.04, and it compounds daily. So the number we're going to put underneath the 0.04 is the number of days in a year, which is typically known as 365. So we have 365, and we want to know how this is going to work out. You want to have this much money for 5 years. After 5 years, so we're going to put 5 into our formula. So the first thing I'd suggest is taking your 4% and dividing that up by 365. Notice that this has e to the -4. That is not an error. That is not ignored. We are going to go 4 decimal spots to the left. 4 decimal spots will put 3 additional zeros off to the left. So we have 2500 P 1 plus 0.000 1. If we moved 4 steps, so that's 1 step, and then 3 more steps would be your 3 zeros. That would give us 0.0001. You want to call it 1, that's fine, but we talked about 4 decimal spots. 365 times 5 gives us our 1825. So that's how many months there are. It's a crazy idea. That's the number of months there are in a 5-year period. That's how often you're getting money added to your account. So what we're going to do is take the 1.0001, raise it to the 1825, and you see that that comes out to be about 1.202. And we'll divide by that amount. So we're going to take our 2500 and divide it by your ANS, or you could type in 1.2002. So what you needed to start with, the principal that you needed to start with would have been $2,082.98. Now we're going to look at exponential decay. The model for exponential decay, very much like exponential growth, you have the A value like we've been talking about for exponential problems. You have 1 minus because it's a decay. It's less than the 100% amount. So that's where the 1 minus R comes from. You have to pay attention to the word decrease. Does it decrease or does it increase? Does it grow or does it decay? So here we have a television worth $1,200. It decreases 21% every year. So we'll take our $1,200, our 1 minus 21% is 0.21. Not 0.021. You have to move that decimal spot over 2. So you're out here past the 1, then you have 1 step to get in between them and 1 step to get past it. So that's where you get the 0.21. Well, 1,200 times 0.79. 0.21 less than 1 gives you your 0.79. So now we want to estimate the amount after 2 years. What's your TV worth after 2 years? So the amount that it's worth is 1,200. 1 minus, well, we don't have to go back through all that again. We can call it 79.79, and our years are the 2. So 1,200.79, we want to see if it drops by 21%, that means that it's worth 79% for both years back to back, and that gives us $748 is what the TV is worth. Now, if you're going to buy your grandma's TV from her, but you only have $300 to spend, when is that TV going to be worth $300? So the question is, when will it be 300? If it started out at 1,200, again, I don't have to write the equation out from scratch. We know that it's 0.79. And what we're trying to solve for is the t. All right, well, we don't know how to solve for an exponent. Not quite yet. So we're going to use our graphing calculator to go to y equals and do our 1,200 at 0.79 for some amount of years. Now, we all know that when x is 0, the a value is the y-intercept. So we got to get up and over this 1,200 amount, at least to be able to see where it crosses the y-axis. So being larger than your 1,200 amount will allow us to see the rest of the graph come down. And there it comes down. So we want to know, when is it going to be 300? So there's your line of 300. Now we're going to look at the intersection again to figure out just where that is. We could count 1, 2, 3, 4, 5, 6, somewhere around 6 years is a good approximation. So we'll go to second trace, down to intersect. We have our first curve, our second curve, and looking for our answer at 5.88. That's how many years it would take for the TV to drop down to $300. By that point, you probably could save even more than $300, but maybe not. All right, last few questions to go here. Here we have an exponential growth. We're going to identify the initial amount, the growth factor, and the percent of increase. Three different things that we can identify here. The initial amount is always that A value. So that's going to be 6. The growth factor, how is this changing for every calculation? That's the 1.017. That's your growth factor. But the percentage-wise is by moving that decimal spot 2 to the right, turning it back into a percentage. So that's the 1.7. That is your percent that this is changing each time. In this next equation, the initial amount is that A value, is that value out in front of the parentheses. So 925. The decay factor, you know this is decay because it's less than 1. The decay factor is 0.62. But the percent that it's decreasing by would be 1 minus 0.62, which is going to be 38. So it's a 38% decrease every time. So they did 1 minus 0.38 and they came up with 0.62. That's where the 0.62 came from, because it had a 38% decrease. So we'll pause the video. You go ahead and work yourself through these 3 problems. Then we can turn it back on and you can check out what the calculations were and how you did. So for example, number 1, we have 1970, the population of Kern County in California was 330,000 people. The county population grew at an average rate of 2.4 per year. Write an exponential model for the population. Let T represent the years since, and that's a key term in there, since 1970. So we're going to have Y. We have our starting point of 330,000 people. And we have 1 plus the amount that we're increasing by. And we're increasing by 0.024. Because it's less than 10, it's going to be 0.0. More than 10, it would be point that number. And then T, and that T is going to be the year since 1970. So there would be the model to represent this problem. Now, if we want to figure out the population in 1990, we subtract those years, and you see that it's 70 years for us to get there. So in 20 years, did I say that wrong? A 20-year difference. So we're going to grow at this rate for 20 years. So we have 330,000 25,000 at the rate of 1.024 for 20 years. So we're going to have 530,289 and a little bit extra people. I like the exact value just to show that you did the actual calculation and you weren't some decimal points off, meaning that you did something weird in the problem and didn't just round it to approximately. Next, we have a new car. And the new car apparently is decreasing. That tells you how to write your equation. This is a decreasing model. So we have a $25,000 car, 1 minus 0.15. And there's your 25,000. And it's going to be worth 85% each year compared to the previous year. So if you want to know what is it worth after 3 years, let's say you lease the car for 3 years. You're plugging a 3 in for your years. So you have your 25,000 for your 0.85 for 3 years. That gives you 15,353. And a little bit of cents left over. That's how much the car would be worth. The auto companies call that a residual value. There's probably more calculations involved, but that would be an average way to help you figure it out. The big question is, what should your decrease be? And that's what years of running an auto place would start to give you ideas on what it is actually worth. All right, here you're going to deposit $1,500 into the account, and it's going to pay 3% compounded daily. And we want to see what will the balance be after 2 years. So 3% has to be in there as 0.03. It's compounded, so that's why we're using the R divided by N. So you might want to first start out with 0.03 divided by 365. So that is your actual amount. It's very teeny, 0.00082. We'll move 5 decimal spots over. So 1, 2, 3, 4, 5 is where that's putting that in at the 8.2. And then we have 365 times 2 gives us 730 as our exponent. So 1500, 1.00008. Now, if you wanted to go up, you could use this exact amount right there. Raised to the 730. That's how often you're going to have that increase, because it's compounded daily. Not much going on per day. And your account would have 1,590.20.